Okay, we're going to be doing some logarithmic integration, but these are definite integrals now, and I like definite integrals because there's no need really to back substitute if you can adjust the limits of integration, and that's what makes these really nice. Okay, so when we get to the end of this problem, you're going to see why in maybe a college algebra course you learned laws of logarithms. Okay, so you'll have a greater appreciation for those laws and why you did them in a college algebra course or an algebra course. So let's take a look here. I'm going to pick my u to be x cubed plus 3x, and I'm going to pick my du to be, well, I can't pick my du, it's whatever the derivative of u is, so it's going to be 3x squared plus 3 dx. Well, I don't see that there necessarily, but you have to rethink the way that it looks. Factor out the 3. You have x squared plus 1 and then dx. So the x squared plus 1 is definitely there. Okay? It is definitely there. What's missing is a 3. So we'll write a 3 right there in the front, multiply it. By consequence, a 1/3 on the outside. All right? Now let's see what we've got. We've got here our du. We've got our u. Now I'm going to adjust my limits of integration. Where x cubed plus 3x was going from 1 to 2, well, all I need to do is plug in the 1 and the 2 into my u, and I'll have my new limits. Okay, so nothing to it there. So when I do that, okay, I plug in the 1, I get 1 cubed plus 3 times 1, well, that's just 4. And then I'm going to plug in my 2. 2 cubed is 8, 3 times 2 is 6, 8 plus 6 rather is 14. So I'm adjusting my limits of integration so that I don't have to back substitute. This makes this really nice now. So I'm going to have 1/3 on the outside, and again with my adjusted limits of integration from 4 to 14, I'm going to get du over u, right? And this fits the form of a logarithmic. Okay, so what you might want to recall, and I'll write this out for you, what you might want to recall is that if you have du over u and you're integrating that, it's just ln of u plus c in this case. But this one is definite, so we're not going to have a constant of integration. All right, so we've got here the natural log, and let me write that in black ink. We've got the natural log of u evaluated from 4 to 14. So what does that look like? That is going to be the natural log of 14 minus the natural log of 4. All right, now I also have to write out the 1/3 out front. I completely forgot about that. So there it is. There's the 1/3. All right, so nothing really to it. Of course, I can simplify this by the laws of logarithms. If you remember anything from the laws of logarithms, subtraction in laws of logarithms means division. And so this becomes 1/3 of the natural log of 14 over 4, which is 1/3 of the natural log of 7 over 2. All right, and so we have our answer. Now, because this is going to produce a positive value, you really don't need the absolute value, but we're going to keep it like that. But just so you know. All right, let's take a look at one more example here. And let me see. Let's pick a good one here. Oh, I know which one we're going to pick. We're going to pick one with some trig in it. All right. And when we do this trig, it's going to be there, but we're going to have logarithmic integration involved here. So it'll be nice. All right, so let's take a look at another one. This one is more challenging. It's always good to have challenging problems, especially when trig is involved. Okay, so we're going to go from 0 to pi over 12. And I believe this is what it should say. Secant squared of 3x dx all over 5 plus the tangent of 3x. Okay, well, this is nice. We're going to call this u. All right, now that I've got my u, 5 plus the tangent of 3x, let's find out my du. Well, the derivative of 5 is 0. Derivative of tangent is secant squared. So we're going to write secant squared of 3x. And then we have to multiply it by the derivative of the inside, which is 3. So then we write our dx as well. So the only thing I seem to be missing is a 3. So I'm going to write my 3. And by consequence, on the outside, a 1/3. Okay, but now we adjust our limits of integration, where we were going from 0 to pi over 12. We're now going to go from where to where? Well, tangent of 0, we plug in. We plug in the tangent of 0, and we're going to add 5 to that. Okay, what do we get? Okay, so go ahead, if you need to, look at your unit circle. All right, find out what the tangent of 0 is. Okay, so hopefully you've had enough time if you pause the video. But the tangent of 0 is just 0. So this is going to be 5 plus 0, which is just going to be 5. And now we're going to find the tangent of 3 times pi over 12. 3 times pi over 12 reduces to be pi over 4. The tangent of pi over 4 is a very famous value. It's just 1 because that's where you have square root of 2 over 2 and square root of 2 over 2. It's the 45-degree mark, or pi over 4 radians. So that right there becomes 1, and 5 plus 1 is just 6. So this makes this really nice now. So now that we've got all of this in play, this right here represents my du over u with my adjusted limits of integration from 5 to 6, du over u. Fix that there. All right, and so what do we get? We get 1/3 of the natural log of u evaluated from 5 to 6, 1/3 on the outside, natural log of 6 minus the natural log of 5, and really there's nothing to it. Again, the subtraction means division, so I end up with 1/3 of the natural log of 6 over 5, and that right there being my final answer. So again, two really nice examples on logarithmic integration, definite integral integration, with some u substitution and adjusting of the limits of integration. So as always, I hope this video was helpful, and remember, like and subscribe.